Okay, fantastic. Well, thanks for having me. It's really great to be able to reconnect with the Meta seminar and the group and all the exciting research that's happening and presented in this series. So happy to present as Sahar says, hot off the presses, long review deliberation, but hot off the presses manuscript, but also some things that led into it, and really in particular methane emissions from landfills. I know. Oftentimes, oil and gas kind of takes central booking to or first priority, uh, whatever the term of phrase is. But we want to talk about landfills. They're a significant source of emissions. So, just to ground this a little bit, landfills, are considered to be kind of third in anthropogenic methane budgets, and this is both in the United States and globally. Usually, not that it's a race, right? But usually considered to be third place in terms of total budgets. Here's just the EPA, inventory, back to 1990 to 2022. And again, you see the wedge for waste, and maybe it's suggestive, a little bit of a declining trend in emissions from the waste sector as well. But it's about 20%. Just let's break that out a little bit just to try to understand, where this is coming from and how they calculate it. I mean, this is an inventory approach, just like the greenhouse gas inventory. A lot of what's used for oil and gas is in this world of emission factor and activity data. I mean, it's similar, but it's a little bit different for landfills in that landfills use models primarily and report emissions to the Greenhouse Gas Reporting Program, GHGRP, through models. And I'll get a little bit more into that. But if you look at how the emissions are calculated over time in GHGRP, really what they're doing is they're taking the individual landfills that report, which is a subset of all landfills, but landfills that report to GHGRP, taking that emission rate, and then they apply this scale up factor for all the landfills that don't report to GHGRP. So anyway, the basis is in models. Now, of course, before the GHGRP, they base it based on some first order decay model on national waste. So if we have some estimate of what the national waste was for a certain year, they say, well, okay, a certain amount of this would decayed into and generated methane, and that's what our emission is. So digging deep into this, and I know I'm like starting, first minute into a talk, and we're already getting text heavy into the Federal Register and reporting protocols, but we kind of have to go there a little bit. And so this is subpart HH, Greenhouse Gas Reporting Program. If you are a landfill of a certain size, and there are strict guidelines on what constitutes a certain size of landfill, you have to report your emissions to GHGRP. Now, there are two ways to report emissions, and they are outlined again in this Federal Register on how you do it. And it's two different types of models. The first one is called a generation first model. And the way you think of this is that if a landfill knows, which they know, how much waste came into the landfill over the course of a year, and they have a record of the previous years, then they can apply a model to it and say, well, a certain amount of that, again, went through, methanogenesis, so it created methane. And of that certain amount, let's assume a percentage of that gas was collected. If we have a gas collection system, capture and collection system, a certain percentage of that was oxidized in the soil, and the rest made it out as emission. That's a generation first model. And the equation is provided in the reporting protocol in the Federal Register in subpart HH. There's another approach, though, which is collection approach. And so this is if a landfill has a gas capture and collection system at the landfill, and they meter how much gas they collected at that landfill, they can say, well, I know how much I collected. Now, if I assume inefficiency, based on how big my landfill was and what cover type I have, I can back out what the emission was, right? So it's kind of going the other direction, right? You're saying, okay, I know how much I collected. Now let's make some assumption to see how much there was emission, because there should be some proportionality there. And the first one is how much did I generate? I start from the waste. Both of these are valid, and landfill operators get the choice. They can calculate both. They get the choice of what they want to report. They're asked to report the highest of the two numbers, but it's a choice. It's not required. Digging a little bit deeper into the models that underpin the generation first GHGRP approach, this is what you get, right? It's just some kind of first order decay, exponential decay. You have some constants here like methane generation rate, capacity, the mass of the waste is measured, you know that. And then you can generate some generation. And then almost all landfills, they assume 75% of the gas is captured and 10% is oxidized. That's the default. And there's other defaults, right, in terms of generation rate that go into, and there's some suggested, if you don't have alternative, there's some suggested defaults that one could use. But ultimately, what you can see here, I have plotted on the left, is that it's a very close correlation, right, to the amount of mass, right? If you put in a lot of mass, you're going to get a lot of mass in, a lot of emission out, so to speak. So of course, there's a lot of work, especially if you're all using the same 75%, there's a lot of uncertainty here, right? Where you could say, well, what if I was 80%? What if I was 30%? How should I be able to report that? And how can I prove something like that? Okay, so you could ask, okay, well, I have this, and then I have this other approach we talked about, which was collection first. What's the self-consistency between the two, right? These are both valid reporting protocols that one could use, right? And so that's what we have plotted here, right? And this is a little bit of a tricky, this is where it gets a little bit trickier, right? The x-axis is what a generation first model would suggest, that equation I showed previously, and the y-axis is the collection first model. So what you can find is that kind of systematically, the generation first models predict higher emissions than the collection first, except for landfills that don't accept a whole lot of waste that year, but have, a history of, some waste previously, so we're still collecting gas. Of course, the collection first models are going to show high emission because they're actually collecting gas, even though the landfills are maybe not accepting a lot of waste. But this now gets into this question, right? If you have a disagreement, and maybe a systematic disagreement, between a generation first and a collection first, what does that do to your assumptions about efficiency in terms of your gas collection at the landfill? What that 75% number, right? It's obviously more fraught than choosing a default. It goes into the complexities of the landfill, which I'll get into, but certainly this is bearing out, just by the models themselves. And you can see, here's an example of where this becomes real clear. A landfill in Texas that for most of the 2010s was one of the higher emitting landfills in the United States in terms of emissions. That's what's plotted here. Then around 2018, the emissions dropped off to make this one of the smaller GHGRP reporting landfills. And so if you looked at a trend like this, you could say, well, hey, this is evidence of reducing emissions at the landfill. And of course, this landfill's contribution is going to go directly into the greenhouse gas inventory. But, right, we know this landfill changed from the generation first model to the collection first model, right? And that's what's driving the trend. So, right, this starts to get really complicated as we think of inventories, we think of numbers, and as we think of that number of 20% of all methane emissions in the US, there's a lot of assumptions that go into this. And landfills themselves are very complicated, right? These are complex, dynamic environments. Every day they're putting new trash somewhere. They can't always put trash in the same place they put it yesterday. They fill up the landfill. So how do you do that? How do you manage it? Let's just break apart a landfill into three components to try to understand this. There's the active working phase. This is where the trash is, dumped actively every day. That will fill up over time. And they may move to another spot of the landfill because they don't want to fill, maybe they could pile more on, but you kind of got to move to different places to fill up the landfill in a smart way. So what'll happen is they'll dump in a active area for a while, then they can put a cover on it, and it becomes intermediate cover, which means you can't touch it for 180 days. And then they will dump somewhere else. Then they might come back to it after 180 days, and they'll keep filling up the landfill. Once the landfill hits capacity, they'll put final cover on top, which means they're not putting any more trash on. And this is where you often see these closed landfills that have golf courses on top, right? Is that they are no longer, or, if you've ever been to Boston, right? Some of the harbor islands used to be these big dumps, so to speak, that they then put a bunch of cover on top. And so there is final cover there. Of course, there's still going to be some methane generated, under there. So, you'll oftentimes see like some gas collection that might happen for closed landfills. But even open landfills will likely have a section of it that is final. Okay. Also for, in the US, to give some numbers, 1,200 landfills, about 1,200 landfills report emissions to GHGRP, and there's about 2,600 landfills total. Okay, so now we go a little more complex. This is the question when we talk about emissions, right, that you often get of just like, well, why don't you just collect all the gas? And it's like, yeah, yes, but it's very complicated, right? A landfill operator has a lot of choices they have to make, and they're not obvious. And it's very complicated. They have to balance a lot of priorities at the same time, right? So an operator on any certain day says, okay, I want to collect my gas, or the gas collection, company that's coming in to design this, say, I want to collect my gas. Where should I install my new well, and when do I install it, right? In fact, and if do I install it in a place that I know is going to have new trash deposited there in a couple of weeks, or do I not, right? How deep do I install these wells? How many wells do I install, right? Think of it, you have buried trash, amount of buried trash that is generating methane. Where do you put it? When do you put it? When's it going to start, creating this methane, and how do you do it? Then once you have this collection system in place, you say, well, how much do I pull, right? They call it pulling on a well, but it's the applying vacuum, or sucking gas out of the landfill. Now you can imagine a case where you say, well, you should pull really hard on the well to suck all of that gas out of the landfill. But you do that, you're going to have some problems. And, they're manifold. One, the most immediate, is that you could suck a lot of oxygen into your landfills. Now imagine if you suck a lot of oxygen into a place where there's a lot of methane. It's kind of your chemistry 101. You're going to create potentially some really optimal environments for combustion. So you don't want to do that, right? But then imagine you also understand that, landfills it's under that buried trash. It gets pretty gross. There's a lot of water there. It's called leachate. So you suck really hard, you pull really hard on those wells, you could pull a lot of water into the wells and flood them, and you might break them, right? And so now all of a sudden you've created a siphon to siphon a lot of gas out of your system that you're not collecting, and that gas that would have remained under the cover is now being emitted to the atmosphere. There's also another question of purity of the gas, right? If you want to process gas and send it down into the pipeline, you want it to be good quality gas. The harder you pull, the more that oxygen or other constituents are going to enter into your gas collection system. So if you want to maintain a high quality of your gas, you have to decide all of this. So these things all come into play. Once you've installed it, first you have to decide where to install it and when to install it, but then you've installed it, how do you actually operate it? It's very difficult. And then once you've done all of that, how can you assess how efficient your system is? It's a lot of work. So let's get to the monitoring, right? We get to the, okay, well, how's this thing working? And what protocols are in place to monitor emissions? So in the US, under the Clean Air Act, large landfills are required to perform quarterly monitoring. This is called surface emissions monitoring, and it's called surface emissions monitoring. There's actually no explicit tie-in to emissions quantification. Think of this more as like concentration hotspot monitoring. If you have an area of high concentration on your landfill, you're trying to do something to mitigate that. Again, think of this as under the Clean Air Act. And so these are generally what's happening is these are walking surveys. And so someone has a backpack that you can kind of see in this picture. They have a little wand, so to speak. Think of it as like a straw, and they're walking around the landfill with a, flame ionization detector. And if there's a high elevated concentration of like 500 ppm, it'll signal a hotspot that gets registered. Has to be some follow-up action. But you can imagine how this can be very difficult in many ways, primarily from the operation of that wand, right? You can imagine the reading would be very different depending on how you're orienting that wand close to the ground. And then two, the topography and danger that you might encounter at the landfill. So look at the plot on the right. These areas of final cover, which are all nice and green, you're able to really walk super well continuously along the landfill and probably get a systematic reading. As soon as you get into the active part of the landfill, where you have these large slopes, or you also have these big dump trucks that are actively dumping trash and might over big hills and might literally run into you, which has happened with these guys before. It's very dangerous. You can imagine it gets harder to have a good reading. And you can actually see in this active area of the landfill, there is not a lot of reading compared to the closed areas. So there is another question of, okay, you're trying to detect hotspots. How will the walking surveys even work? And again, there is no tie-in to emissions quantification. So this is the current reporting protocol. So I'm bringing all this background up because it does seem to suggest that there's some needs for baselines, emission baselines, and something to verify whether or not the modeling is working or the hotspot detection is working. This is kind of where the airborne remote sensing comes into play. Where I'll start this talk is that there's this impetus for measurement-based broad area baseline surveys. So a lot of this work from airborne remote sensing platforms happened as part of the Cal Methane survey in 2016, 2017, flights done in California using aircraft, operated by NASA JPL, imaging spectroscopy technology. So for those not familiar, deploy on an aircraft an imaging spectrometer. So, visible to shortwave infrared, 300, 2500 nanometers, 5 nanometer spectral sampling, which it can image at about 3 meter spatial resolution, and is very sensitive to the methane absorption around 2300 nanometers. So the idea is that if you image in this way and there's a high methane concentration, you can see that. And that's what these false color plumes are on this map of identifying high concentration methane. And so this survey, tried to at least survey most, not all, but most of infrastructure across all sectors in the state where there could be high concentration gradients of methane, or you call them super emitters, but something that is abnormally high emissions. And so this on the bottom, you'd see a landfill plume in particular. So not necessarily, and I'll show this can be used to quantify an emission rate, but the idea being you're trying to detect high concentration gradients of methane emissions, which are then used, can be used to quantify an emission rate. So again, this just comes from that paper, the supplement of that paper. So on the plot on the left, here's a plume of high concentration. You can apply some, IME / cross-sectional flux approach. There's many approaches that people in the remote sensing community use to try and quantify an emission, right? So quantify the amount of excess mass due to the plume, normalize it by some lifetime of the plume. So you can think of something that can resemble a flow rate in kilograms per hour or seconds. These measurements for quantification have been tested under several environments. So the plots on the left were done during the CalMethane survey with simultaneous observation with scientific aviation. I'll have more on that in later, where we've done more expansive surveys. But the blue bars representing scientific aviation, the orange representing the average NG emission rates, and the dots representing, or the diamonds representing, the reported EPA annualized emissions. So that's a little fraught because it's an annualized versus an instantaneous, but or a single overpass, whatever you want to call it. That's what's on this first panel. On the right is asynchronous. So some landfills or other sources where they weren't observing at the same time, but observed multiple times over the course of weeks to months, and they take these averages. And so it's showing correspondence. Scientific aviation is a little more of a flux mapper. Again, I'll get into that, than carbon mapper. So you wouldn't necessarily expect, or average NG, you wouldn't necessarily expect average NG to be higher, so to speak, than scientific aviation, but it could be the same under cases where the only emission source is a point source. Later, we've done blinded releases, right? And so, Sahar obviously spearheading lots of these in the Stanford groups to apply, specifically this California methane survey method against blinded releases, and we don't see a huge amount of bias. Of course, there's high uncertainty, but in aggregate, not a huge amount of bias. And of course, as you get more information like wind speeds, et cetera, the fit improves. But using this information, it's showing it's a fairly unbiased result in aggregate. So again, just don't want to belabor too much, but the Cal methane survey flew over 400 solid waste sites and detected, point sources, or, some call them super emitters. It's a fraught term, at 32 of the sites, and that sector of the quantified emissions in that survey, the landfills made up the most. And you can see that the distribution also is shifted higher relative to the other sources. But again, landfills are big, right? And there's a lot of methane being generated. So that's not totally inconsistent with what we may have thought, but again, it's bringing a observational baseline to it. This data wasn't just used for baselines. This was used to help prompt mitigation as well. So here's an example of a landfill in Southern California that we flew during that survey. And I apologize for so many color bars I'm going to swap as I pull from different papers during this talk, but here's a red-orange color bar. We detected very large methane plumes on the first overpasses there. They were doing some ongoing mitigation efforts due to high odors in the community, but we provided this data to them, said, look, you can isolate probably some of the problematic areas to here. The local enforcement agency and the operators used that. They then went to figure out, like, why were we getting so much, methane here? And it's kind of a complicated story, but it goes into antecedent work practices, mainly the way that you layer trash along a landfill. There's federal standards of how much cover you can put in between those layers, and really in the daily cover, basically, okay, it's just real quick. Every day you dump some trash on the landfill. At night, they cover it up with something called daily cover, which is usually soil. And they don't do this for methane. They do it so that, coyotes and birds don't run in and scavenge a lot, or rats. And then at the start of the next day, they peel the cover back, they put more trash on. Well, 10 years ago at this landfill, they weren't doing that. And so you were getting, what you might call a garbage lasagna, where you're getting these stratified layers of dirt, trash, but that meant that the leachate was having a hard time percolating to the bottom of the cell, meaning you were generating a lot of methane towards the top of the slope, and they think that was what was leading to higher emissions, at least their hypothesis. But over the course of a year, they then underwent some pretty expensive remediation efforts. So putting two things, one called posi shell, the other is closure turf. Posi shell is cement fiber that they sprayed on top of the landfill. Closure turf is astroturf, right? Is artificial grass that they put on top of the landfill. But they also installed, 50 more wells. And we were flying the whole time, and we could see that the odor complaints in blue from the community were kind of decreasing along with the methane that we were quantifying at the landfill. So it's a proof of concept that, you can use this type of data with high spatial resolution to prompt mitigation and verify that that you're having the intended effect. Okay, so that kind of set the stage a lot for future studies where we said, okay, well, we saw a lot in California, but what is the prevalence of these large localized emissions? I'm saying large localized emissions instead of super emitters, but if that's more convenient, you could think of it in that way as well. It's again a little more fraught in landfills compared to oil and gas, but you can imagine the fact that it's localized as being the key part here. What are the prevalence of the localized large emissions at the GHGR reporting landfills across jurisdictions and climates? How persistent are they, and how do they compare against total emissions and GHGRP emissions? This is the backbone of the surveys that we then undertook afterwards, which were, it's kind of funny, like you spend a lot of time mapping oil and gas regions. You can map a lot of stuff over the course of the day, but landfills are more sparse. So, it took a lot longer to fly a lot of these, right? But we ended up flying, 250 GHGRP reporting landfills across the US. So 20% of all of the GHGRP landfills, but also sampled them to be kind of a little bit more in the higher zone. So meaning that this is 67% of all the emissions. So we observed landfills that are thought of by the bottom-up inventories to be 67% of all the emissions, averaged 6 flight per landfill. Some of the landfills, especially the ones in California, because we kept flying them over the course of this time period, we got 50 overpasses, right? Other ones, maybe 10 to 15, and then some were in transit, so it was 1, but the average was 6 overflights. And the fact is we saw these localized emission sources at 52% of the sites. So 52% of the GHGRP reporting landfills had the strong point source. When you compare that then against GHGRP, again, the sampling caveats, keep those in mind, you see no real correlation between the two. In fact, no correlation. And you can see some emissions that we estimated that are below GHGRP, but then there's this body of what looks like kind of systematic bias up landfills. There's also no correlation in terms of trends for the landfills that we've observed a lot. Of course, these are California landfills because we were observing back in 2016, but GHGRP here, representing a flat trend where we are seeing, increases in emissions. Again, sampling caveats apply, but when you're looking at things that are 4x higher over the course of a few weeks, over the course of a year, you have to start wondering about this. But going back to this bias that we see here, and going back to what we talked about in terms of reporting approaches, just think of this shape that you're seeing here, aerial emissions against GHGRP, and then think of if we were to compare that large bias of our aerial emissions against the collection first models. Think way back to the second slide or third slide I showed, where we said it seemed as if the generation first models and collection first models were showing a systematic bias, with the generation models being higher than the collection first models. If you break out our aerial emissions against the collection first models, you actually see a similar trend, right? Maybe showing that the collection first reporting might have, again, we're in hypothesis space, but might have an issue here in terms of total reporting. And that's not replicated with the generation first models. There's no correlation with the generation first models, but there's also no bias, right? And so you improve the models, but it's not as if our aerial emissions are falsifying that the generation first models are completely biased. And, maybe with a more concrete example, let's come back to this landfill the Seabreeze landfill, where we saw this evidence of the high emissions that then went way down, and it went from generation to collection first. Of course, I bring this one up. We did observe, right? And so we looked at this one. We've sampled it many times. Here are plumes that we saw. This is persistent. We actually, have seen this over the course of, many months and years now, even with the EMIT satellite. But, much higher emissions than what it's a different unit, but than what the collection first model would represent. This is also an important case because we can use the high resolution visible imagery, and maybe it's not super obvious here, but if you also overlaid some even higher resolution visible imagery, you would be able to tell that this is the active face. This is the dumping part of the landfill where there's trash, the working face of the landfill. And this is an area where there's no gas collection. You can't really collect gas if you're actively dumping trash. You're going to run over your wellheads. You're going to have problems. So oftentimes, if they're putting a working face on top of an area that once had gas collection, but they're filling that up, they'll turn off those gas collection wells. And so the fact that we see presence of emissions here is a little bit maybe indicating, right, where a collection first model might have trouble. Because if you're seeing a large emission source in an area where you're no longer collecting gas, that would be something that would kind of evade that collection first model unless it was explicitly put back in. Okay, again, we'll get more into attribution in a second. But let's go now to the second question we had scientifically, which was, persistence. How persistent are the emissions? And so what I have plotted here is detection frequency. So, how often do we detect a plume by number of overpasses? And the blue dots are the landfills in our study, and the green dots is if you take previous work we've done for oil and gas in the Permian, and you find in the Permian, as you kind of fly more and more, you start to get at this converging detection frequency that's maybe hovering around 0.2. When you do that with landfills, it's maybe hovering around 0.6. So by and large, we're seeing much more persistent point source, localized emission source activity at the landfills. We can summarize that in another way, though, using this unit. I know it's not totally obvious, or maybe not the easiest to interpret, but what call here the time scale, or you could call it the duration of point sources. So the idea being is that if you have a time series of overpasses of a landfill, and you can calculate the time period between your first detection and your last detection, and you assume that it kind of persisted between those detections, and hopefully you have a time series in between to corroborate that. If you take that as your numerator and your denominator is the total time you observed it, you can look at like some sort of time scale, some like normalized time scale of that source. And what we find when we do that with the landfills, and for the landfills where we've at least observed them across 100 days, so there's at least 100-day spacing between first and last observation, is this bimodal distribution. This actually comes up in oil and gas as well, but the idea being is there's a population of highly intermittent events, and there's a population of super persistent events, right? Unlike oil and gas, with oil and gas, when we do this, we find it is about equal, the highly intermittent event and the highly persistent event, in terms of emissions and in terms of number of sources. So the take home from that is that if you go after just the persistent ones, which are probably abnormal, which are true kind of process failures, you could get at 50% of the point source budget. Here, what we're finding is that the persistent ones are 60% of all of the sources, but they actually make up 80% of all the emissions. So they're quite a bit larger. And so you would actually realize a larger benefit if you were to really look at those landfills where there was persistent point source emissions, as they're a bit outsized. Another point that we wanted to test here, both for validation, but for understanding point sources, is to expand the scientific aviation overpasses. And so here's just two examples. This is simultaneous observation, where with Carbon Mapper, which is our plume here, and then scientific aviation, they fly these circles. You think of it as like a coffee can on top of a facility, but they fly these circles of varying altitudes, and they integrate along that path to come up with a mass balance total flux rate. And you can see, at least visually, the corroboration that at the same time the plume that we're detecting at the landfill, that downwind concentration is elevated, and it's happening in both of these cases. So we did these coordinated flights with scientific aviation in coordination with Office of Research and Development at EPA, specifically regions 4 and 5. So this is Michigan, Ohio, Georgia, Alabama. This is, far away from California, and quantified emissions. And this is what we're getting on this plot at these landfills. And so what's interesting here, again, is that, they're all pretty consistent within the uncertainties, and the correlation's pretty good. But, what has us scratching our heads a little bit, which merits, I think, further investigation, is, well, how much do the point sources actually make up against the total emissions, the total flux from the landfill? So, scientific aviation, you can think of it more as quantifying a total flux. It's getting everything within those rings, the upwind versus downwind, the contribution of all sources in there. Whereas we're calculating that point source, discrete point source, but what we're finding is they're giving us about the same answer for both. So yeah, again, more investigation, but the idea being is that, if point sources are present at the landfill, are they really dominating the emissions? There's a lot here that needs to be tested, but you can start thinking of, various hypotheses in terms of, if you kind of designed a landfill to be very effective at collecting gas, so you can go into your gas collection system, but then there's presence of an emission or something that would lead to a point source emission, it might be very efficient at emitting in that way. Again, something that could be tested, but that would, be consistent with seeing a point source dominate the total budget. Okay, so there was that, but then now getting back to attribution, it gets a little bit more complicated with landfills compared to other sectors where, for example, you see a plume coming out of an unlit flare is pretty obvious. And maybe that happens in a landfill, and I'll show that later, or you see something coming off of, pick your piece of infrastructure of choice, right? But it's a very discrete, localized point source. You can say, I think there's a problem there. Obviously requires follow-up on the ground to really isolate the issue, but you can pinpoint it. A little more complicated at landfills, because landfills are a little more complicated. You can think of it as lots of things that are about in the same area can cause an emission, and all these things are very small scale. So, like, for example, if you detect a very clear plume like this one, it's a very, large clear plume, but everything in that circle, whereas your possible origin of the point source could be the result of a crack in your cover, right? So imagine that it hasn't been raining for a while and the dirt starts to crack. Well, now you've opened up something where an emission can escape. You might have that broken wellhead. It could be flooded, like I was mentioning before, and there could be an issue. Someone could be doing maintenance to gas collection system, right? And so during maintenance there's an emission, or similarly construction. So all those things can happen. It's really why it's important to get at the handoff between the remote sensing and really attributing the processes that are happening on the face of the landfill, so we can better design best practices that have a observational and empirical baseline to corroborate. There are some cases, though, where it's very clear, and I kind of hinted at this before. So here's a landfill in Louisiana where we detected lots of emissions. And you can see on the plot, the larger plume to the west of the landfill is quite massive. And you could say, well, that's a huge problem. And it is. But the one that kind of is a little bit, I don't know if it's worse, but is a tricky one, is this plume here to the right, to the eastern portion. So if you zoom in there, what you can see is this is a facility, gas collection facility. And right here is a thermal oxidizer. So it's, kind of supposedly supposed to be functioning like a flare, but we see this big methane plume coming out. So it's, it's not quite an unlit flare, but you can essentially think that the oxidation is not happening if we're seeing a methane plume. And the fact of the matter is we flew this landfill a lot over the course of a year, and we always saw the plume here over the course of a year. You can average the emission rate that we got and integrate it over a year. If you integrate that, that would be, 1,300 tons of methane. And for context, in Louisiana, the GHGRP for that state is, 117,000 tons. So this, which should be oxidized entirely alone, if you assume the GHGRP value is about right, that would be, 11% of the entire state's waste GHGRP, because lack of oxidation. So again, showing where remote sensing can maybe point to something and there can be follow-up, so that things that should be functioning, the one on the left is harder, right? It's a bigger plume, it's a higher emission rate, but it's harder. The one on the right should be kind of slam dunk, especially if you're collecting the gas. Okay, I'm gonna pivot a little bit more now into ongoing work that we're doing, which really gets at this attribution question in particular, which is, can we, how fine scale can we go from using the remote sensing data along with some visible imagery and anything we can get from ground information to try and understand different practices and how they lead to emissions. And so thinking in particular to what I talked about before of gas well, one is gas collection systems that are happening not on the face of the landfill, but more at facilities like this, so like RNG facilities. What are the detections we're getting there? But then also honing in on this working face issue. And so again, when I showed you that sea breeze example, the idea being there's a big, large working face emission. So in 2023, so actually we've now left my paper, and these are landfill flights we did in 2023, and we flew another 217 landfills. So now we've flown over 400 landfills that report to GHGRP. We took all of the data from these, and where we could make an attribution to the active working face of the landfill, we would attribute a plume to that if it was in close proximity after consulting with contemporaneous high resolution imagery. There's many landfills where we were able to do it. There's other landfills where it could have been from the working face. We just could not make that determination from where the plume was oriented or what the flow looked like relative to where the working face was. But at least for many of these landfills, we're able to make a pretty clear attribution. Kind of stop there, and then for everyone on the call, put in a plug that you should do this on our data portal as well, and please do this. So here's an example on our data portal right now, live. You can go to it, right, data.carbonmapper.org, where you can toggle these layers if you open up a sidebar between the contemporaneously retrieved RGB imagery and also not just the plume mask, but the raw concentration mask. So like if you were to click on one of these, you would get the raw concentration mask. You could then toggle that in between the high resolution imagery. You could then, look at a high resolution base map, although it would be asynchronous, to try and do your own attribution to this. Okay. Had to put the plug in. But if we do this type of analysis and do that attribution, what my colleague Tia Scarpelli is finding is that the workface emissions, which again is an area that is basically outside of those Clean Air Act regulations for surface emissions monitoring because it's so dangerous, and it's an area that's very hard to quantify under the existing greenhouse gas reporting protocols, are quite prevalent in these landfills where we detect large point sources. So this light, yellow is where, of the landfills where we are detecting things where we are finding workface emissions, right? So, and this is a little bit, you can imagine it's a little bit perplexing on first glance because this is an area where active trash is being dumped. It's not like a lot of methane is being generated by the time it goes to your trash bin at home to when it's first dumped on the landfill. There's a lot of oxygen. Unless that's really gross stuff that's going into the landfill. But you got to think that, landfills, they are trying to fill capacity along the landfill, and they can't just build a huge trash mound on one place and move somewhere else. So they're kind of distributing it along the landfills. It means you are burying new trash generally on top of old trash. So if you can think about when that intermediate cover comes back off to put new trash on, and you've maybe shut down those wells that were collecting gas because you don't want to break them or because it's hard to collect, now you've opened up potentially an area where emissions could come from. Again, hypothesis space, but it seems very consistent with how you would think gas might want to escape on an area where there was once older trash. If you look on the plot on the right, this is now comparing again to GHGRP, and what I think the big take home here, like the other one, isn't necessarily, again, that there's a big underestimate in GHGRP if you, consider the caveats with sampling. But the point is that it's very predictive that a landfill will have higher emissions than what's predicted by GHGRP if they have workface emissions. So if there is a workface emission identified at a landfill, it's very probable that that landfill is emitting at a rate that's higher than what GHGRP would anticipate. And that's an important finding because, again, these are emissions, and it's consistent. These are emissions that aren't readily captured within GHGRP protocols. Okay, fun stuff. So I'm now want to move to the what's next, right? And get a little doom and gloom about some of this stuff, but I showed that Sunshine Canyon example. It can work. We can mitigate emissions, but we also have to do this, we have to scale this. We have to do this we have to have sustained monitoring. I mean, you're going to get, the temporal variability of emissions requires a sustained monitoring solution, and it's a global problem, right? Okay, of course, okay, in the United States, it is a significant contribution of emissions. You can also think, I won't get too much into the politics, but you might imagine that some states that are more reflective to climate goals are going to be states that have waste, right? Because every state has a lot of waste because everyone generates trash. So you can kind of think of that as well in terms of priorities. But the point is, we're scaling this up to satellites. Of course, probably many on this call are very familiar with many point source imaging spectrometers that exist out there, including NASA EMIT instrument on board the International Space Station. So this is technology that is kind of the next generation of the airborne hyperspectral instrumentation that we flew in these airborne campaigns, and it's been imaging since 2022 across these target regions, which are generally arid dust regions. They are expanding the scope a little bit more, but generally speaking, that's the primary mission of it. But of course, in these regions, it's a pretty big swath globally. There's a lot of waste as well as other emission sectors like oil and gas. And so here's the example that gets shown a lot in Turkmenistan of big complexes of plumes. So we have gone through that record and looked at kind of systematically looked at global waste sites, where at least we know, that's another big problem to all this. We don't actually know where all the global waste sites are. I mean, it's like, there's no good GIS on this, but in places where we have pretty good confidence that there's, waste there and have seen clear evidence of plumes from EMIT, we've been able to quantify them and are starting to build out, analytics that look like this. And so I know on people's screens, it's probably hard to see, but this is the different countries on the y-axis. And this is the bar is both, number, the blue bar is the number of plumes that we found, and the hatched is like the number of unique landfills that we were able to image. We should probably have another bar here that's harder to do, which is what are the total number of landfills that exist in that country that we know of, right? To get to a more comprehensive understanding as we do these comparisons. But then you can start taking things like the plot on the right and saying, okay, what are the emissions, right? And how do we rank the emissions? And if we do attribution, this is colored by attribution, what are the emissions coming from? What types of activities are the emissions coming from? So basically, we need to scale the Sunshine Canyon story globally, right? And so that will just bring me to my last slide, is the Carbon Mapper Coalition, where it's both a nonprofit that I pertain to, which is, public good mission to deliver actionable data, methane and CO2 data publicly to prompt mitigation, and to hand off to people who have on the ground expertise to prompt mitigation. But there's a broader coalition, and this is a public-private partnership between us, Planet Labs, JPL, RMI, and others, which is to build satellites designed for this use case, as well as other hyperspectral use cases. And so you think of the airborne campaigns, EMIT being the next generation. The satellites that we're building with Planet Labs and JPL would be the next generation of the EMIT sensors, although they're still full hyperspectral, they are more optimized for methane and CO2 remote sensing. We have a planned launch for later this year, the Tanager satellite. So if you hear Tanager written, that's what it's called. And the long-term goal here, as this progresses, to be able to track, kind of 90% of the point sources, and the data is publicly available. Go to our website. Just end with the major conclusions here of, the inventories say about 20%. Maybe that's right, because we're finding stuff in other sectors, which is showing it's maybe higher as well. So who knows what the actual is? Maybe 20% is right, but we are seeing, we'd certainly know that number is not really based in comprehensive atmospheric measurement. So it needs to be, right, at least as a backstop, right? And that because the protocols that are used, at least in the US, for reporting, there's no real harmony between the two. And that's, a bit problematic. We're finding large localized emissions, both in California, but also in these expanded airborne campaigns that we've done. That's pretty prevalent at the large landfills, 52%, and it's pretty persistent. And with the inner comparison with scientific aviation, it seems like the point sources really dominate the total flux. And again, the shout out to we have to do this in a sustained system, which is probably from what we think is from orbital platforms, in addition to other things on the ground. Really, it's not just one satellite. It's a multi-scaled approach, but you need to have sustained measurements So okay, yeah, I'll leave it there, and then happy to answer any questions. See, there's some in the chat. I haven't looked at them.
Yeah, great. Thank you so much, Dan. That was a really excellent talk. Shall we stop the recording?
Yeah, that'd probably be good.
Philippine.